So, welcome everyone for the next seminar on probability in stochastic process from USP. And today we have Andressa Cerqueira from Federal University of São Carlos. And Andressa is an old PhD student from here from IMI. And she's going to speak about Gibbs random graphs for us today. Welcome, Andressa, and thank you for accepting the invitation.
Thank you, Aline. So first, I would like to thank you this opportunity to be here at IMI, right? Even that's just online, but for me, it's a real pleasure to be here. And I'm not seeing the face, but I can recognize some names here in the audience that was important for me when I was a PhD student. So I'm really glad to be here. So today I'm going to talk about spatial Gibbs random graphs. And first, I would like to give some motivation for why we are interested to study this kind of random graphs. So here we have an example of a graph. I don't know if you guys can recognize, but here we have the shape of Brazilian map. So the red dots here represent the airports in Brazil, and the gray lines represent the connections, the flights between these airports. So we can represent real data. For example, this real data from airports has a graph or network, depends what we want to do with this kind of data. And we can analyze these kind of graphs using like 2 points of view. So if you are a statistician, we can think about a statistical model where we are going to think about problems of infer the parameters of the model, or like doing hypothesis testing for the model, or for example, if you want to cluster the nodes of the graphing groups. But if you work from a probabilistic way, we can think about define a probabilistic model and then study asymptotic properties of this model, existence of this model is some other kind of properties that we can think about. So I have been working the 2 point of view here, doing my master, doing my PhD, postdoc. But today I would like to talk about the second point of view when we are looking at graphs from a probabilistic point of view. So as a motivation, we have a random graph model that's well known, and it's called Exponential Random Graph Model. That's the IRGMs. And I will give some idea what's this model here. So first, just to have some notation, I'm going to represent the graph by its adjacency matrix X, where each entry of this matrix will give me if I have a connection between a pair of vertices or if I don't have this connection. So if I have an edge or not between a pair of vertices. So in this exponential random graph model, we have that the probability of observing a graph is given by this formula here. So we have a probability that's proportional to the exponential of a theta, and an x function here. So the thetas here, it's a vector of parameters that we are using to represent this model, and S represents a vector of statistics of the graph. So as a statistics, we can think that, okay, suppose that I would like to model some network where I'm interested in counting how many edges I have in this network. So as a statistic here, I can use edges. Or if I would like to study, like, for example, for social networks, for example, I have 3 people here. This guy is friend of this guy, that's friend of this guy, and it's friend of this guy. So I can model the network using triangles. Or if I expect to have this kind of structures that we call stars, for example, this guy is friend of this one, and this one is friend of this, but these guys here are not friends. So we can use stars to model the network. There is some message for me, or... in the chat?
Yes. Large X is a matrix, small x is a graph.
Okay, large X would be like the random graph, right? And the small one is the observed one. This is the difference of capital X and the small x here. So capital X for us is just the random variable. Okay, so this is the idea of exponential random graphs. These graphs are widely used for analyzing social networks. So there are a lot of kind of works that we can think about this. For example, inferring the parameters theta when we observe a network, or some other related problems like hypothesis tests and so on. So the idea here is that why I'm introducing this model, because if we look this model, this is, for us, it looks like a Gibbs measure that we have on the set of all possible graphs, right? So, okay, suppose that here, I come back to the example, we can think that when we have a network like this, we can think that it can be more likely to have an edge between pair of vertices that are close to each other, right? Because we can think that, okay, maybe it's more likely to have a flight between airports that are close than that's very far away. Because if I want to go, for example, for this airport here to this one, I can just stop in the middle of the way and then take another flight. So there are some kind of networks, real networks, that we can have this kind of exercise that we are looking at the distance between the edges, between the vertices. So thinking about this, we would like to define a model that's quite similar to this one, where we are going to have a model that takes in account structures in the graph, for example, numbers of edges, triangles, stars, clustering, whatever. And also we are going to use the information of how far is the vertex of the graph. Right, so this is the model that we call spatial Gibbs random graphs. So in this talk, I will focus in two works. The first one, Gibbs random graph sum point process, and the second one is the work that I did with Professor Nancy Garcia from Unicamp. So I will focus on these two works because they have like results that's quite similar and it's nice to compare. So let's define now what's the spatial Gibbs random graphs. So now I would like to take in account the distance between vertices. So I need that my vertices now should be in a metric space. So here I'm going to consider Z2. So V will be the set of vertices of the graph, and it will be a finite subset of Z2. Here's just a notation of all possible graphs that I have in this space, so all possible graphs that I have with vertices set V. And now we need to define the length of the edge, or the distance between the edge. So for an edge I and j, we are going to define the distance between this. So if I take vertex I and vertex j, I have an edge between them, and then I call this distance between these two pair vertices. I just use the L1 norm to define this distance here. But okay, of course, we can think about any kind of distance that you're interested in, depends on your space, but here we are going to use this one. All right, so the model that we consider here, that we define, is just a Gibbs measure. So we have a finite set of vertices V, and we define this measure here when the Hamiltonian now of this Gibbs measure is given by this formula. So let's understand what we have here. First, just a parenthesis, but here, suppose that I have a parenthesis here and parenthesis here. So the sum is just over this first part. F is not in the sum, right? So the Hamiltonian here that we are considering, this first part here will penalize graphs with long edges. Because here, you see that beta is a positive parameter, so here we have minus beta, so we are going to penalize long edges in the graph. And this function here is the function that we are going to use to describe what kind of statistics we are interested to look in the graph. So this function can be any kind of statistics that we would like to see in the graph. So it can be number of triangles, number of stars, some function of the degree of the nodes, can be any kind of function. But actually, it's not any kind of function, should be a function that satisfies some properties that I'm going to show now. So before to define the properties that we need, let me define what is a modified graph. So suppose that we have a graph. So here it's a small one because suppose that it's fixed. We have already observed this graph. So suppose that we have this graph X. I'm going to define xij1 and xij0. What's that? I'm going to pick two pair of vertices I and j in the graph, and then the graph I and j1 will be the graph X, but I will put the edge I and j in the graph. And the graph X I and j0 is just the same graph, but now I'm removing this edge in the graph. So the idea here is trying to see, in some ways, we are trying to track what's going on when we just change one edge in the graph. So we are trying to control this. What's changed in the function f, this function f here, when I change just one edge in the graph. This is what we want to track. You are going to see why we just look at one. So the functions that we are going to consider here are functions from the graph, any kind of graph to the real line, such that when I look the difference of the function, when I have the modified graph, when I have edge ij in the graph, and when I compute the function, when I have the graph without this edge I and j, this difference here will only depend on edges that are connected to I or are connected to j. The other edges in the graph do not matter. The second assumption that we need is just a lower bound for this difference. So if we look at this difference here, for all possible pair of vertices that we have in the graph and all possible graphs that we have in this finite set of vertices, this is lower bound by this constant n. So this is just the two assumptions that we need for functions f. So one question here that may arise is that, okay, but is there some kind of function that satisfies a1 and a2? So I'm going to give some examples of functions right now. So the first example is the model that is defined in this paper here that we are going to talk about in this presentation. In this work, the authors define the function f has a sum over all possible vertices in the graph of this phi function. What's this phi function? So this phi function here is a function that is proportional to one constant, a positive constant h0, when the degree of the graph of this node is equal to 0. This function here is proportional to 0 when the degree of node I is equal to 1, and this function fi is proportional to degree of node I when the degree of node I is greater than 2. So in this model, they are using, let me just come back here, they are using the same Hamiltonian. So sometimes I'm just omitting this part, but this part is always fixed in the Hamiltonian. And they are using the function f here as the sum of these phi functions. So by this part, we know that that model is penalizing long edges, right? So this model is penalizing long edges by the first part. And by this function here, what this model is doing is in some way, he's favoring vertices of the graph with degree around 1. So I'm trying to penalize nodes with degree greater than 2 or degree 0 in this model. Because here, if you can see that this phi function is proportional to degree of node I, so as large as this degree, more we are penalizing. So we don't want to have this kind of configurations. Okay, so let's see if for this kind of model, the assumptions that I made are satisfied. Well, when you look at the difference, remember that we need to look at the difference when I have the graph with the edge I and j, and when I have the graph without this edge. This is just the function, the difference between the phi functions for node I and the phi functions for node j. Okay, if we just analyze this difference for node I, so this difference here, we have this expression. I'm not going in details how to get this expression here, but what's interesting to analyze is that if we look at this difference here, this difference only depends on the degree of node I, right? Because here depends on degree of node I, and also here in this expression depends on the degree of node I. So basically what we are saying is that this part, this difference, only depends on edges that are connected to node I. This is the same for this part here. This difference will always depend on edges that are connected to node J. So basically, this difference is exactly what we want, is that this difference of f's depends only on edges that are connected to I or connected to J, or both. Also from this expression here, we can see that the lower bound for this difference, because this is for fixed I and j, but doesn't matter, doesn't change if we change the node I and j. So the lower bound for this difference is given by minus 2h0. Basically, it's just this minimum here will be minus h0. Here, for this difference, will be also minus h0. So we have 2 times h0. So here it's an example that I like because it's not like trivial, right? We have a function that depends on the behavior of the degree of the nodes, and the function is satisfies the condition that we want. Okay, let's move on to the second example. All right. So this example here, we are going to try to define statistics that is kind of similar with the statistics that we use for exponential random graphs. So here I'm going to look at true stars. So I would like to look at true stars, but I also would like to penalize the length of the stars. This is why I have here the length of edge I and j in jk. And here is how many true stars I have in the graph. This is what. So this part here will be the function f, right? So when we look, we are going to look at the difference of function f here. So I put here a figure to see what happens. So suppose that I fix I and j be equal to, let me see, 1 and 3, right? So I and j now, the edge that we are going to put and remove from the graph is this red edge here. So if this red edge is in the graph, you can see that we have the star 1, 3, and 6, this star here. And we also have the star 3, 1, and 4, right? We have this one. We also have more true stars in the graph. That's 4, 5, and 6, 2, 6, and 5. Okay, when we look at this difference here, so now if I remove the edge, the red edge, I will lose the star 1, 3, 6, because this red, I remove this red line, so I lose the star 1, 3, 6, and I lose the star 3, 1, 4. So all the stars that is changing in the graph is that ones that is formed by edges that are connected vertex 3 and the edges that are connected to vertex 1. Because, for example, the star 4, 5, 6, there is no connection with 3 or 1, doesn't change, right? Remains the same. So basically what we are saying here is that when we look at this difference only depends on connections that I have with vertex I and j. That's what we want. So if we just write this difference formally, what we get, like doing this difference, is just like I'm going to look at all connections that I have with vertex I. Also, I have here the length of these connections, and all the connections that I have with vertex j, and also using the length of these connections. So this is the first assumption that we need. The second one that's not difficult to see is that when I minimize this function for all possible vertices and all possible graphs, I have that m is equal to 0. So again, we can both conditions that we want are satisfied. Okay, so this is the model. This is the kind of functions that I would like to study in the model. But I didn't say yet what we want to study in this kind of model. So what we want to study is like, okay, I define the special Gibbs random graphs for a finite set of vertices, right? So we have V is a finite set of vertices of Z2. But actually, our question is, what happens when I'm looking at an infinite number of vertices? So you can think that we have now an infinite graph, have an infinite number of vertices. So I would like to study this infinite volume Gibbs measure that I will call through this presentation as me. So we have the special Gibbs measure me V when I have V a finite set. If me for us is when I'm looking to the entire space. So I have that V is equal to Z2. I would like to know if this measure exists, if it's not unique, or what kind of properties this measure has. This is the question. So to answer this question, I would like to come back to this paper from 2010. So just to be, okay. So in this paper, as I said before, the authors define the model that's the semi-Hamiltonian. So the first part penalizes the length of the edges, and the second part is this function phi that depends on the degree of the vertices. So this function here, just as I remember, is kind of trying to favor nodes with degree 1 in the graph. So we are trying to penalize nodes with degree 0 or degree greater than 2. So one of the results of this paper here, to be honest, they have more results, but the result that I'm going to talk today that's related to what I have is that the measure me can be constructed as the limit along the subsequences of finite measures me v, when v is going to Z2. So we can define, for example, v has boxes in Z2, and then we can think that I send this box going to infinity, and then we can construct this measure me. So, okay, that means that this measure exists. And what's interesting here is that, okay, so we have a measure in an infinite graph. What kind of properties we can have? So if we have an infinite graph, we can think that one node can be connected with infinite nodes. So we can think that we can have infinite degree in this for graphs generated by this measure here. But what's interesting in this result is that the part that I think is more interesting is that they prove that actually when the constants h0, h1 that is used to define this function phi here is positive constants, the measure me, so the infinite, when I'm looking at the measure in the infinite graph, is actually concentrated on the set of all graphs with finite degree. So we don't have infinite degree in this infinite graph. I think this is interesting. And this actually happens because we are penalizing long edges, right? So when we have an edge that wants to be in the graph, but this edge is very, very long, we are penalizing this kind of edge. So this is the intuition why we have this concentration of the measure of graphs with finite degree. They have studied, I will say a few words at the end of this talk, what else they proved in this paper, because the focus of the paper was, I think, different results, but they didn't mention anything about the uniqueness of this infinite measure. Okay, and now what we did in this work is, okay, using the same model, the spatial Gibbs graphs, but now instead of look of this function here, we are going to look for any kind of functions that satisfies condition 1 and 2. So we are in this kind of models. Here it's kind of more general. We define this function alpha beta, that's a function of beta, and the function of the lower bound that we have in the assumption. So here is how is kind of the relation of what I'm going to show with the function f, because the lower bound of this function, the difference of these functions, appears here in this alpha of beta. Okay, we are going to define a beta star. That's the minimum value of beta such that this alpha beta is smaller than 1. Okay, what we prove in this paper is that when we are looking models with beta greater than beta star, we can guarantee the existence and also the uniqueness of the infinite Gibbs measure mean. So here we can also guarantee uniqueness. And what we also have here is that the finite measures converge weakly to the measure, the infinite measure, and also that this measure is concentrated on the set of all graphs with finite degree. So as you can see, there is a relation between these two works. Here, the only difference that we have a kind of beta critical where we can guarantee the uniqueness. And also that here we are looking at more models. So we can have any kind of function that satisfies the conditions. And remember that this function here also satisfies the condition. So basically what we have is that there is a beta critical for this model that I forgot to put here, but I have the expression of this one for this model, but I totally forgot. And we can also guarantee the uniqueness for the previous work. So this is the results. What I'm going to do now is give an idea why, or actually not why, but how we could guarantee the uniqueness in this case. So basically here was an idea. The idea here, okay, let's see how I'm saying something wrong. It's wrong time to say that. Okay, let's see how we are going to do this. So the idea here, look at it. What we have here is kind of a static network, right? I'm just looking at one graph. And I would like to define a model when I have an infinite number of vertices. This is what I would like to do. To do that, I would like to I need to define a Markov process on the set of all graphs. So now I will construct a kind of evolution in the set of graphs. And how I will do this dynamics in graphs. To do this dynamics, I'm going just for each time, I'm going just to change one edge in the graph. This is why I was just looking at the difference when I have or when I don't have the edge in the graph, because at each time of this process, I'm just going to change one edge in the graph. And in which way? So how this dynamics works. So I will add or remove an edge. To add an edge, I will have a graph at some time, and then one edge, I and j, will try to born in the graph. So the edge will say, hey, I would like to be part of this graph. So the edge will try to born in the graph with this rate here that's proportional to the length of the edge and also proportional to the lower bound that we define for the f function n. But this edge is trying to be added in the graph. But this edge will be only added in the graph with this probability here. So first, the edge tries to be born in the graph, but I will just put this edge in the graph with this probability here that will depend on the current graph that I have. And this probability here will depend on the lower bound n, and also the difference of the f functions that we know by assumption that this difference here only depends on edges that are connected to I and connected to j. So basically, these probabilities here will only depend on the edges that I have in the graph at some time that are connected to I and j. Okay? So I need that assumption to try to control things in the graph, to try to control these dynamics. This is why I have this assumption 1. Assumption 2 appears here, because basically by assumption 2, I have that this is a probability. Okay. And remove edges is simple. I just will remove an edge of the graph with rate 1. So adding edges is more complex, but remove is just at rate 1. So what we have is that for when V, the set of vertices is a finite set of vertices, it's not hard to show that the invariant measure of this process is just the measure that we define, because we construct the process to be like this. So basically, to construct this measure, we can just construct this process. But what we want to do is construct this measure when we have an infinite set of vertices. And this is the point that we are going to use a different kind of construction. So the construction that I'm going to use here is a construction based on a graphical representation of this process that we have here, that I define here. And in this graphical representation was used before. Here are 3 works that introduce this representation. And this representation gives rise to one idea of clan of ancestors of the edges of the graph that I'm going to explain how it's interesting for us to use this idea of clan of ancestors. So, okay. Okay, so let's move on to the graphical representation. So here, this is my attempt to draw the dynamics here. Let's see how it works. So here, I have the 2. I have the pair of vertices I and j and jk. I'm just going to look at these 2 edges and form 2 pair of vertices in the graph. So what I'm going to do is to define an independent Poisson process for each edge in the graph, for each possible edge in the graph, actually for each pair of vertices. I'm going to define a Poisson process with the rate that I have defined before. So it's the rate that this edge will try to born in the graph. For each time that the edge try to born, I will call these times like t. So for this edge I and j, t1 ij was the first time that this edge tried to born. Here was the second time, here the third time. It's the same thing for jk. T1 jk is the first time it tried to born, and so on. Here it's not very intuitive because I'm thinking that 0 is here, and I'm going to positive like this, not going up. I don't know why I construct in this way, but just explain. So this is like time 0, and positive is going down. Okay, so for each time that the edge try to born, I will associate how long it will survive in the graph. So to do that, I will define an independent exponential random variable with mean 1. Because if you remember, we are removing edges in the graph at height 1. So here we have these exponential random variables that describe how long each edge survives. So basically from this idea, we can have this representation of this process using rectangles. Because here, for example, we can think that I have a rectangle such that the basis of this rectangle, I will say that's the edge that I'm looking at. The birth time of this rectangle is the time that of this one here, this one that I'm looking at, is the time that it tried to born. So it's, in this case, it will be T1 ij. The death time will be how long it survives. So it will be T1 ij plus S1 ij. So it will be this length. It will be like the height of this rectangle. I don't know if the height is the correct word.
Andressa, this S variables could be smaller than the difference between T1 and T2, right? Or not?
Yeah, could be. Yeah.
Okay.
Yeah, it could be. Yes, but in my figure, I was very biased.
Yeah, this is why I was.
I did it in the easier way, but yeah. And so it will be the death time, and the lifetime will be just the interval here, right? That this edge will be alive. So using this definition, we can define a random family that's a family of rectangles. That's given by this construction where I have the basis, the time that it tried to born, and how long it survives. This is the family that we are going to look at. So here's just to say that if we fix a time interval, st, I have this rst will be the set of all rectangles that was born in this time interval. Okay. All right. So now how we can construct the process using this idea of rectangles here. So when v is finite, and I'm fixing a time interval 0t, for example, I have this set of all rectangles that was born in this time interval. Here, I forgot to put the line here of 0, but imagining a line here, such that the basis of this rectangle, it's part of vertices when I'm looking vertices in the set V. So we have a finite set here. So since V is finite, we can order the occurrence time of births and deaths of these rectangles that we have. So we can order all the marks, and then now we are going mark by mark and see what we are going to do in the graph. So suppose here that Rm, let me see. Okay, this Rm here is the birth. Let's look at this one. Okay, don't look at the red one because it can be the death mark of this one. But let's think that this is just the birth mark of this blue rectangle here. Okay, so Rm is the birth mark of this rectangle. So what we are going to do, since it's the birth mark of this rectangle, that means that this edge, jk, is trying to be added in the graph. But I'm only going to add this edge in the graph depends on the configuration that I have. So I need to put this edge in the graph with probability that depends on that probability Q. If you remember when I defined the probability Q, what we have is that this probability only depends on edges that are connected to J or connected to K. So basically what here we have this idea that, okay, so basically, to add this edge in the graph, basically I need to look all the rectangles such that the bases intercept the bases of JK, and that was born before JK. So if we think about rectangles, we can think that like this. So this is the set of rectangles that I need to look in the past to see if I'm going to add or not JK in the graph. All right. But when Rm is a depth mark, that's simple. When it's a depth mark, I just remove this edge in the graph. If it's not in the graph, it doesn't change anything, but we just remove this edge if it's in the graph. Okay, so this is when V is finite. When we do this, we can construct the Markov process that I defined before. But the problem here is that when V is finite, we know that the measure exists, everything is fine. But what we want to do is when V is infinite, when V is our Z2, for example. So in that case, we can't construct the process like this because we cannot order the marks because we now have an infinite pair of vertices, so I cannot say what mark was the first one. So I can order the marks when V is infinite. So I cannot do this kind of construction here. But this construction gives us the idea that I just explained, that was, if I want to define if an edge with basis ij will be add or not in the graph, I need to look all the rectangles that has bases that intercept I and j, because this comes from the difference of the function f's, remember, to compute these Q probabilities. So first thing I need to look of all the rectangles such that the bases intercept I and j. So this interception here is not empty. All the rectangles that was born before, right? Because this will say how is the configuration of my graph. And all the rectangles that was alive at the birth time of this rectangle R. Because, for example, just come back here to this picture. Let me put here. When I have here a birth mark, this rectangle here doesn't change anything to decide if this edge will be added in the graph or not, because this rectangle just was born after this rectangle here. So I don't need to look at the rectangle that was born after, just the rectangles that was born before. So this idea here gives us the idea, the idea of clan of ancestors, because I need to look all the ancestors to decide if the edge will be added in the graph or not. So we can think here ancestors of a rectangle. So what is an ancestor of a rectangle? So we can define, for example, if here I'm going to define ancestors for one vertex, but we can also, in the same way, we can define ancestors for edges. Doesn't change anything. Okay, so for vertex I can define the first generation of this vertex I, that will be all the rectangles such that I belongs to the basis of this rectangle. So just come back here. So if I'm looking, for example, vertex J, the ancestors of a vertex J, I need to look at all the, for example, connections I in J, JK, J, and other vertices that we have here. And so such that the I belongs to the base of this rectangle and the rectangles that are alive at this time t here. The second generation will be just the first generation of the first generation. So all the rectangles that belongs to the first generation, I will define the ancestors of these rectangles. Okay. And In that way, we can define all the clan of ancestors by the first generation, the second generation of ancestors, the third, and so on. So we have here the entire clan. So what we have, the result that came from the papers that I showed before. It's known by the construction of the clan of ancestors that if with probability 1, all vertices of the graph have not an infinite number of ancestors, then the Markov process that I defined before can be constructed from -infinity to infinity in such a way that the invariant measure of this process is μv. This is true when v is finite or infinite. So this is nice because now I can construct my process when I have an infinite number of vertices. So just to give an idea why this result is important, because we can use the clan of ancestors, we can define a branch process that dominates the clan of ancestors, and then we are going to look at this branching process and see when it dies. I forgot how to say this. You know, we don't have any other generation. So when it happens, we know that since it's dominate the clan of ancestors, we know that we don't have we will only have a finite number of ancestors for vertex I. This will happen when that function that I defined before, the alpha beta, is smaller than 1. So this is an important thing. So when this function is smaller than 1, so that was the way that I defined beta star, I can guarantee that I can construct the Markov process when v is infinite. Also by this result, since I can construct from -infinity to infinity, I can construct a preferred sampling algorithm in such a way that, suppose that I would like to know at time 0 if I'm going to add a vertex, an edge or not in the graph, and then I'm going looking at the past, looking at all ancestors until at some point, since the clan of ancestors is finite, I don't need to look anymore to the past. In such a way, I just do some kind of cleaning in the process, and then at time 0, I can guarantee that I have some configuration, originate from the invariant measure of the process, so from the measure that we would like to have. So just here, just to put everything together. So this is why this beta star appears here. This is to guarantee that I have a finite clan of ancestors. And by having that and construct a preferred simulation algorithm, I can guarantee that I have the uniqueness of this measure because I'm constructing this measure so it's unique. So we have both things at the same time, existence and uniqueness. The second part here, this part, to prove this one is also using a dominating process. We construct the same kind of process, like just for come back here, the same kind of process, but instead of just the edge try to be born, and I will see if I'm going to add this edge or not, I just remove this part here, and every edge that try to born in the graph, I just add this edge in the graph. So now I will have a graph with a lot of edges, so this graph is dominating the process that we want, and for this dominating process, it's easier to prove that the measure is concentrated on graphs with finite degree. And then this is the same for our process, because the other process that dominates the process that we are interested in. So so this is the idea how we did this construction. I bring this construction because I think it's very powerful. It's not new, right? I show you guys the papers that have used this construction before, but they never have used this for graphs. Okay, so here just to make some comparisons, talk a little about what we can think about of new results for this process. That okay, in this paper here, now to be fair with the authors, what they did is consider actually V on RD, and in our paper we just look at V on Z2. They also consider that V it can be fixed or can be a sample for homogeneous Poisson process. We did not do that. I think it's a nice how can I say next an interesting point to think about, because here in this paper, remember that they just look at the model with these 5 functions, and here I have more general functions. So it will be interesting to see what we have when V is also sampled from homogeneous Poisson process. Actually, in this paper, I think the authors were more interested in percolation results. So that means like existence of infinite cluster in the graph. They have results in this direction. We didn't. So I think this is also interesting to look when we have like more general functions, since we know that for more general functions this measure exists. So I think it should be interesting to investigate also some percolation results for this kind of models. And we also have more results about mixing time of the measures in EV. We have some central limit theorems, but didn't put here today, otherwise it would be like crazy. That's all for today. Thank you.
Thank you, Andressa. Do we have questions or comments?
Yes, I will have 2 questions, Andressa. My first question is, if you can have some information. So you said that the degree of every vertex is almost surely finite. Can you have an information on the distribution of this degree?
No, I don't. I remember that I have some kind of upper bound for the expectation. I don't remember, but the expectation is very low. So it would be like around 2, you know, so it's almost empty.
Okay.
This is why the things worked.
Okay, and the second question is the condition you have on the second function. So you have the dependence on the length, and you have a function. This function, if there is no such function, you can do. I mean, you can take away the function f of your Hamiltonian, or you need it to get your coupling argument.
What condition? You mean this one?
No. I would like to know if you can just consider the Hamiltonian just with the length, without the function fb. This is okay with your conditions. There is no problem, because it seems to me that you have an m, your condition on m. What is it? Can you come back to the condition on m?
This one, right?
Yeah,
this one that depends on m?
Yeah, the m, your m has to be strictly positive, no?
No, not necessary.
Okay. What
was it greater than -1?
Yeah, in the beginning you said that you have a...
yeah, it should be...
between -1 and infinity.
It should be just because to guarantee that I have this beta star. Otherwise, I don't have this beta star.
Okay, so if there is no function, then you have m equals 0, and then it works. Okay.
Yeah, actually, for this case here, that we start to look at this model, 2 stars, m is equal to 0.
Yeah, okay.
So,
And when you consider the stars, you somehow you said that it was the second condition you have on this function, which is that when you look the difference, it only depends on what connects to each one of the you mean there is not another vertex which is involved in this difference somehow? So I understand that when you do your simulation, this is what helps you in the sense that when you want to see the clan of ancestor of just one guy, it just climbs one by one somehow. You had one. You have to look at the first. First in. But if you had to look at two levels, would it be very bad? I mean. Here you said somehow you look just at one level because you said that the difference will only depend on those which are connect to them. But if you look also to those which are connect to those which are connect, you know,
Yeah.
This turns it completely impossible or just a bit worse on the condition at the end. Is it possible or is it combinatorially impossible? I don't know.
That's a good question that I don't know exactly. Because when we do this kind of clan of ancestors, we always need to control things, right? You know that we need to control for things that does not explode. So I'm controlling here how many I need to look. So this is, for example, I will look just for those that are connected to I and J, and also that ones that are close.
That are connect to those one in the past somehow.
Yeah. So maybe
not close in the sense of the distance because there is no reference to the distance. You mean which are connect to. So here J is connect to I and K, say. Then you come back in the past to look whether or not I was connect to who it was connect in the past.
Yeah.
And then who these one were connect to the past, but only one by one somehow. And if you do it 2 by 2, does it mean that it just twice as large somehow the clan of ancestor and it's still almost surely finite or something like that? I don't know.
Yeah, I don't know. It's a good question. Actually, it's something that I should think about. Yeah, I don't know.
Okay, no, that's the only question I had to do. Thank you.
Thank you.
Anyone has any other question? I had a question, but your basically answer, because I would like to know the phase or more or less how the limit graph would be, but you just answer it with very sparse, right?
Yeah, I think it will be very sparse. This is, I don't know, my intuition said that this is why we don't have percolation, but I know this is not really true because we can have sparsity, but we can have percolation some way. But yeah, it will be a sparse graph, and maybe like it's connect.
And my other question is, because you use exponential graphs that actually people like a lot because they use these statistics that you can control, right?
Yeah.
It seems to me that you don't use these statistics explicitly in your clan of ancestrals and your simulation. Am I wrong? Like you didn't use it like you prefer or triangles or nothing like that.
No, yeah. The only thing that the only dependence that we have from the statistics is the n, so is the condition, and that's all. But it makes some sense. Why? Because it's well known that for exponential random graphs, that's why people don't want to look more at this kind of models, because there are some papers, Strategy and Giaconis, they proved that when n goes to infinity, so when we have exponential random graphs and the number of vertices go to infinity, actually what we have is an Erdős-Henny random graph. So basically we are losing all the structures, the dependencies in the graph. So here maybe the same thing happens, right? Because here the structure of the graph is not we don't have dependence of the structure of the graph in the limit when we have an infinite number of vertices. So maybe there is some kind of relation between these two models. So just to say that this also happens when we look at exponential random graphs. So when you look at exponential random graphs and send the number of nodes going to infinity, we have some measure that's very similar with Erdős-Rényi random graphs. So everything is independent.
So in your case would be Erdős-Rényi with a very slow degree, right?
Yeah, I don't know if it's Erdős-Rényi.
Yeah.
But
strategy says that it's Erdős-Rényi.
Yeah.
So if you don't have any other questions or comments, let's thanks Andressa again, please.
Todo mundo ficou calado agora, né?